In February of this year, 3 telescopes pointed at the same patch of sky 300 million light-years away in the Perseus galaxy cluster confirmed something that should not exist. A galaxy with almost no stars, 4 globular clusters, ancient spherical swarms of stars, each containing hundreds of thousands of suns, were sitting together in a tight grouping. Around them, a faint, diffuse glow so dim it had escaped every telescope that had ever looked at that region before. Hubble found the clusters, Euclid confirmed the glow, and the Subaru telescope in Hawaii helped rule out every other explanation. The object was designated Candidate Dark Galaxy 2, CDG-2. It shines with the light of roughly 1 million suns. For comparison, the Milky Way shines with the light of roughly 30 billion. CDG-2's 4 globular clusters account for about 16% of its visible content. The other 84% is an extremely faint scattering of stars too dim to resolve individually. And the mass holding all of it together, the gravitational glue preventing those clusters from flying apart, is estimated to be 99% dark matter. This is the first galaxy in history detected purely through the presence of its globular clusters. Dai Li of the University of Toronto, who led the discovery, said it directly. This is the first galaxy detected solely through its globular cluster population. Francine Marlowe of the University of Innsbruck, who analyzed the Euclid data, said the images demonstrate the mission's unique capability to detect new low-surface brightness galaxies, including extremely faint ones. And the telescope that made this possible, the one that confirmed the ghostly glow around those 4 clusters and revealed what was hiding in the darkness, is the same telescope that 3 weeks ago discovered 31 of the oldest quasars ever found, including 2 that were already blazing when the universe was just 670 million years old. Stay with me, because the Euclid Space Telescope is doing something that no instrument in history has attempted before. It is mapping the invisible architecture of the universe, and what it is finding is rewriting how we understand everything from the smallest hidden galaxies to the largest structures in the cosmos. Euclid launched on July 1st, 2023 from Cape Canaveral and traveled roughly 1.5 million kilometers to Lagrange Point 2, the same gravitationally stable point where the James Webb Space Telescope operates. It joined Webb and the Gaia telescope in orbit around a spot that keeps the Sun, Earth, and Moon permanently behind it, ensuring they never interfere with observations. It took 23 countries, 80 companies, 300 institutes, and 3,500 people to build, and it was designed for a single purpose: to solve the largest unsolved problem in physics. Roughly 95% of the universe is missing. That is not hyperbole. It is the central fact of modern cosmology. The visible matter we can detect, every star, every planet, every gas cloud, every atom in your body, accounts for approximately 5% of the total mass energy content of the universe. Another 27% is dark matter, an invisible substance that does not reflect, emit, or absorb light, but exerts gravitational pull on everything around it. The remaining 68% is dark energy, the name given to whatever is driving the accelerating expansion of the universe. Nobody knows what either of them actually is. Euclid was built to map both. Not by detecting them directly, which is currently impossible, but by measuring their effects on everything we can see. Its primary tool for mapping dark matter is gravitational lensing. When light from a distant galaxy passes near a massive object on its way to us, the gravity of that object bends the light, distorting the shape of the background galaxy. If the alignment is perfect, you get an Einstein ring, a complete circle of redirected light surrounding the foreground object. If the alignment is slightly off, you get an arc, and if the lensing is subtle, spread across entire galaxy clusters, rather than concentrated around a single massive object, you get what is called weak gravitational lensing, a statistical distortion in the shapes and positions of thousands of background galaxies that only becomes visible when you analyze the distribution mathematically. That weak lensing signal is the primary way Euclid intends to map dark matter across a third of the entire sky. In June 2026, the mission published its first demonstration that this technique works. Scientists confirmed that Euclid can trace massive structures dominated by invisible dark matter using weak gravitational lensing, ahead of the first full cosmology results expected in 2027. If you are the kind of person who stays for the real science, drop a like right now, because it genuinely helps this kind of content reach more people who want to hear it. The scale of what Euclid is producing is difficult to hold in your head. By late 2024, it had completed roughly 1% of its planned survey. That 1% already contained 100 million sources of light, either individual stars or entire galaxies. The full map, when complete, will cover more than a third of the sky and record data on approximately 2 billion galaxies. The data is measured in petabytes, hundreds of them. A petabyte is 1,000 terabytes. Your computer at home likely has 1 or 2 terabytes of storage. Euclid's final dataset will require the equivalent of nearly 1,000 high-end computers just to store, and buried inside that ocean of data are patterns that no human eye could ever find on its own. Weak lensing signals, Einstein rings, dark matter filaments, the gravitational fingerprints of structures invisible to every other instrument. Finding them requires artificial intelligence. Machine learning algorithms are being trained to identify gravitational lensing candidates across the petabytes of imagery, a task that would take human volunteers generations to complete manually. In April 2026, ESA launched Space Warps, a citizen science project on the Zooniverse platform, inviting the public to help spot strong gravitational lenses in Euclid images alongside the AI systems. The combination of machine learning and human pattern recognition is expected to uncover thousands of lensing events that will allow scientists to map the distribution of dark matter across billions of light years. Now let me walk you through what Euclid has actually found so far, because even with only 35% of its survey complete, the discoveries are already extraordinary. In October 2024, Euclid released its first batch of science images dubbed First Light. Among them was the Perseus cluster, 240 million light-years from Earth, containing more than 1,000 galaxies. In that single image, Euclid discovered over 630 previously unknown dwarf galaxies, tiny faint galaxies that had been overshadowed by brighter neighbors and were invisible to every telescope that had looked at that cluster before. Those dwarf galaxies matter because cosmological simulations predict their existence, but previous instruments could not find them. Their shapes and distribution relative to the cluster and background galaxies are exactly the data scientists need to determine how dark matter is distributed. Finding 630 of them in a single image was a breakthrough. It was in this same Perseus cluster data that CDG2, the dark galaxy, was later confirmed, hiding among thousands of visible galaxies with almost no starlight to give it away. In June 2026, Euclid turned toward the center of our own galaxy and produced the largest and most detailed photograph ever taken of the Milky Way's core in visible light. The mosaic captures more than 60 million stars in extraordinary detail, taken in just 26 hours of observation time. Euclid's ability to differentiate between individual stars in the densely packed galactic center, where most telescopes are blinded by the sheer concentration of light, gives scientists a baseline they will be able to use for years to come. When NASA's Roman Space Telescope, launching August 30th of this year, later observes the same region and detects a microlensing event, the moment a planet's gravity briefly magnifies the light of a background star, scientists will be able to compare the total mass measurement against Euclid's earlier data of just the star, making the planet's mass straightforward to calculate. And then, 3 weeks ago, on July 6, 2026, ESA announced that Euclid had discovered 31 of the oldest quasars ever documented, more than doubling the number known from that early stretch of cosmic history. 2 of the 31 are the oldest quasars ever observed, shining when the universe was just 670 million years old, roughly 5% of its current age. Each one is powered by a supermassive black hole weighing approximately 1 billion times the mass of the Sun. Joseph Hanawi, a co-author of the study published in Astronomy and Astrophysics, called them monsters weighing billions of times the mass of our Sun that somehow already existed when the universe was in its infancy. He added that we do not yet have a good understanding of how they grew so massive so fast. It took a decade of previous work by other telescopes to find roughly 10 quasars from that era. Euclid found 31 in a single year of survey data. Antonio Lamarca, an ESA research fellow on the team, said the result more than doubles the number of quasars we know of from that cosmic epoch. Valeria Petterino, ESA's Euclid project scientist, described ancient quasars as time machines that enable us to explore the early universe and understand how the first generation of galaxies came to be. Here's what I want you to take away from all of this. Euclid is not a telescope designed to take beautiful pictures, although it does that almost as a side effect. It is a machine built to answer the largest unsolved question in physics. What is the 95% of the universe we cannot see? It maps dark matter through gravitational lensing. It traces dark energy through the expansion history recorded in the positions and redshifts of billions of galaxies. And along the way, it is finding objects that were invisible to every instrument that came before it. A ghost galaxy made of 99% dark matter detected only because 4 ancient star clusters gave it away, 600 dwarf galaxies hidden in a single cluster image, 31 quasars from the first 5% of the universe's existence, each one powered by a black hole that grew too massive too fast for current models to explain, and a mosaic of the Milky Way's core containing 60 million individual stars captured in a single day. The survey is 35% complete. The first full dark energy and dark matter cosmology results are expected in 2027. 4 more years of data remain. And every batch so far has made the picture of the universe stranger and more complex than it was the day before. Somewhere in the petabytes of data Euclid is still collecting, there are patterns we have not recognized yet. Filaments of dark matter connecting galaxy clusters across billions of light years, the gravitational fingerprints of structures that no telescope has ever mapped, the shape of the invisible scaffolding on which every visible galaxy in the universe is built. We are about to see that scaffolding for the first time, and what it looks like may not match the blueprint we have been drawing for the past 25 years. If this kind of deep, research-grounded science is what you come here for, subscribe right now and turn on notifications. Euclid's first cosmology results are coming in 2027. Roman launches in 5 weeks. I am covering every piece of it. Drop a comment with what surprised you most and share this with someone who needs to hear it. Thanks for watching, and I will see you in the next one.